Namaskar. Welcome to Prakash on Basics. I'm Prakash Zog. We saw last time that uranium 235 is the main source of all nuclear energy, a source that will grow with time. So, we must have a proper understanding of what this uranium really is. Let us try and do that today. Let's look into the what, where, when, why, how of uranium. And let's break it down into one or two areas. Uh, we have to understand that uranium was discovered as a as an element in 1789 by Klaproth. He was a German scientist. And at that time, Uranus was the planet that had just been discovered. So he named the element after Uranus as uranium. But it was practically 1938 uh, when they realized that uranium could be used as a source of fuel. Where does this uranium come from? Its origin is actually interplanetary, uh, like all other metals and elements. When supernovae explode, the very high temperature and pressure that is developed results into formation or conversion basically of hydrogen and helium into heavier elements. The most heavy of that lot really existing for a long time is going to be uranium, as we know from the periodic table. So when earth was formed, like all other elements that accumulated on earth, uranium too came to earth and became a part of earth itself. We must realize that uranium is not a rare element. It is present in the innermost area of earth, region of earth volume, which is known as the core. It is on the layer on top, which is known as the crust. It is also in seawater, that is all around us. 70% of the earth's surface is seawater. uh, Actually, it is the highest element with Z value that is found naturally on earth. What is Z? Atomic number, something that I talked of last time. And for uranium, it is 92. Uh, as far as how much it is, considering all the elements, it is 48th most abundant element on in the crust of Earth. It's more than tin, more than lead. It is more than cadmium. It is more than mercury. In fact, it is more than silver also. So you'd find that it is not a very rare element as such. In the Earth's crust itself, it is said to be 2 ppm, that is 2 parts per million, and that's for the whole surface of Earth. The crust, which is quite a big thick layer, that then is more than one of the common elements that we know of, which is tin. In seawater, it is estimated that there could be close to 4.6 billion tons of uranium in seawater throughout all the oceans. And suppose we extract all this uranium and use it as fuel, then the energy that it will produce will exceed all the deposits of fossil fuels that we can ever recover on Earth. So later on, in the long run, uranium is going to be a major source of energy. Where is it found? It's found in Canada, it is found in Nigeria, Russia, Kazakhstan, Namibia, uh, Australia, Uzbekistan. As far as India is concerned, we import it from the Kazakhstan region. Canadian ore is said to be pretty good because the ore is has roughly 15 to 18% of uranium, which is a very high, good quality of material. Mm, Uraninite is the most common ore of uranium. That's a technical name, but the common name that is used for it is known as pitch blende, which is actually a mixture of oxides, uh, uranium dioxide and U3O8, which is a very important area. This It's basically impure U3O8 and other materials that are mixed along with it. There are other ores also, potassium, uranium vanadate is one of them. Then calcium uranium phosphate is another. And this phosphate has a different way of extraction. We'll keep that aside right now. What about its physical and chemical properties? Some of them must be known and understood. It's basically a radioactive element. So that is why we are talking of it in this section of radioactivity. As far as the periodic table proposed by Mendeleev, uh, this is in the actinide series in the periodic table, which is in that F block that is there below. This is meant more for people from chemistry and physics who know about periodic tables and so forth. Um, its density is around 19 grams per cc. That means 19 times heavier than water. Mercury is 13.6, so it's heavier than mercury. Iron is only around 7, 8 point something, 7 point something. Lead is 21, so it's close. It's a heavy metal. It's silvery gray in nature, and it's ductile. Ductile means you can draw it out into very thin wires. The best of that category is, of course, platinum. And it is malleable. That means it can be beaten down into sheets, like that silver foil that we produce by beating it down, or gold foils that are produced. Same way, even this can be beaten down. That means it is malleable. Uh, Chemistry-wise, its valency is 6. There are lower 2, 3 also, but 6 is its standard because it has 6 valence electrons. And therefore, uranium hexafluoride is one of its major compounds that we will talk of, not today, but sometime later on. Mm. And as far as magnetism is concerned, it is slightly paramagnetic. Para is partial, so it is partially magnetic, but it is weak paramagnetic substance. And I also told you that uranium has 92 protons, so naturally its atom will have 92 electrons, and this will give you a solid metallic structure. Number of protons obviously is going to be 146, and the total of 96 and 146, 92 and 146 will be 238. That's why it is uranium 238. Last time I talked of isotopes, and I talked of only two isotopes, which is 235 and 238. But actually, there are quite a few isotopes of uranium that are present in the ore. 99.3% of all uranium that we look around is uranium 238. About 0.72% is uranium 235. Uranium 234 is also very small trace, 0.005%. And uranium 236 and 233 are very low, so nobody really talks of them. There's one more isotope. It is uranium 232, but it is said to be a synthetic element. That means it has to be only produced in laboratories, and it remains for a very short time and dissipates. Uh, we need not know all the numbers and all that. But realize that as you go down from 238 downwards, the number of neutrons will keep on decreasing, like what we talked of last time. And what about half-life? Actually, the very fact that we find uranium in a large quantity on Earth implies that its half-life must be pretty large. Half-life of uranium is uranium 238 is 4.5 billion years. That's practically the age of Earth. So what uranium got accumulated on Earth at that instant, half of it is still there. So that's quite a bit of uranium. Half-life of, of uranium 235 is zero point 0.7 billion years. Remember the problems I talked of about half-life some time back. So zero point 0.7 and 4.5 implies that there would be 4.2 will be about 6 times, which means it will become 1 of half, 1/4, 1/8, 1/16, 1 upon 32, 1 upon 64 of the original amount that will remain. So obviously uranium 225 is going to be pretty low on Earth, but that is the one that is more important. So we would be more interested in finding and getting this uranium 238. So it has to be obtained from the ore itself. Uh, right from the time it is extracted, used, depleted, and reused, there are many important steps. And these are known, this forms what is known as the uranium cycle. Today, let us look into the earlier part, the initial part, which is extraction and refining of uranium. Uh, it has to be mined, and this mining and extraction is done by three main methods. The first and the most important one today is what is known as the in situ mining. That is mining where it is, uh, at the location site itself. Then the second method is conventional mining, where tunnels are dug deep down, the ore is extracted and taken out. And if the ore content is very close to the surface, you don't have to dig down, you just make a pit. This is known as the open pit method. So these are three methods that are used for many substances, in fact. So for uranium, these three are used. Uh, Nowadays, the most popular method obviously is the in situ ore. But this method can be utilized only if the ore lies in a porous layer that is sandwiched between two non-porous layers. In geology, these layers are known as strata. So you have a porous strata with the ore, non-porous strata on the top, and another non-porous strata below. That's actually the pattern of how things work out in many situations. So it's a very common pattern that is available. So if the ore is in this particular form, then you can use in situ method. What do? You dig bore wells till they reach this particular porous strata with the ore that we are interested in. The wells are what? First type is the injection wells, and the second one is extraction bore wells. So whole lot of wells are dug up. Then dilute sulfuric acid along with water is pumped at high pressure through the injection wells. The name for such chemical is a leaching agent, because what it does is it dissolves the desired ore into itself, or takes it away and keeps the rest of the material where it is. So it tends to dissolve the oxides containing uranium. But along with it, if there are other elements and other dissolvable material, that also gets dissolved. But all the rock and insoluble impurities remain where they are. And so when you pump out this liquid from the extraction well, what you have got is a dissolved solution containing uranium oxides dissolved in it. Rest of the rocks and dirt and other material remains where it is. It is this fluid solution that must be utilized. This is pumped uh, to a chamber where there are very large towers. These are known as ion exchange towers. Um, the whole liquid is treated with ammonium nitrate. Uranium forms ammonium diuranate. I'm just giving you the names. You just understand what is happening. That's all. And this being insoluble gradually settles down. uh, the ions get transferred from the leaching agent in these ion exchange towers. So the leaching agent is free of all this material. So it is then pumped back into the system through the injection wells, and the cycle continues. So you don't really waste the chemicals as such. Uh, but suppose such layers are not present, then the ore has to be mined by the normal method. That means you go deep down, dig tunnels, go horizontally, make branches, and use rock crushers and take all this out. The conventional method, in this conventional method or in the pit method also, the ore is mined out, and very close to the mining site itself is a major milling unit where all the ore is crushed and ground into extremely fine powder. Then depending upon the type of ore, a leaching agent is used. It could be sulfuric acid, which is an acidic material, or it could be an alkaline solution such as sodium hydroxide or something of this sort, depending upon the type of the ore. Um, this then naturally will dissolve all the uranium oxides that are present, and this leaching agent will then be treated with um, again again ammonium nitrate, the same process. So all the impurities that are there, all the clay, the rock, etc., that is there, will remain where it is. So it has to be washed clean, and all that is filtered and separated out. As I said, it has to be treated again with ammonium nitrate, and what you get is ammonium diuranate. This is filtered out. So all that whole cake and material is taken out, separated from the liquid, and dried. Once it is dried, then it is calcinated. Calcinated is a mining term. What it basically means is you bake it at high temperature. Here it is baked at around 850 degrees Celsius. What it does is it converts all this into oxides, and this gives basically U3O8, which is a major component of the triuranium oxide. So this is the major part of the ore that has resulted into a refined material containing only uranium, mostly. Uh, Previously, it used to be called yellow cake, but nowadays, with so many other places where ore is being extracted, sometimes it is found to become black, red, yellow. So that yellow cake common word has now disappeared, and commonly it is now called uranium ore concentrate. That's because this yellow cake has roughly 80% of uranium in it. So this is all dried and filled in steel, 200 pound steel, 200 pounds of each material is put in a steel drum, because basically it's a radioactive material, and then it is sent off for further processing. So the extraction process basically terminates here, where the yellow cake, or UOC, uranium ore concentrate, is extracted, dried, packed, and sent. The next process is not really very simple, it is pretty complicated. So it can't be done at the same place where we are talking about. I also mentioned about a phosphate ore. See, uh, in much earlier days, uh, one of the major uses of phosphates is to make urea and other phosphates that are used as fertilizers. Not urea itself, but along with urea, these phosphates are superphosphates, etc., are blended, and so getting good phosphates is a part of fertilizer industry. But since some of them also contain uranium, the after its processing, the impurities left will contain uranium. So as a byproduct of fertilizer industries, this uranium oxide is also extracted, and because now the costs are increasing, so it is worthwhile. If previously it was just disposed of, Nowadays, that uranium is also utilized sometimes. So this is how uranium gets extracted. If you liked whatever I have said, try and see some slides or things like that on it, so that when you look at it, understanding things will become much easier. How mining is done, how extraction is done is what I have told you today. Like and subscribe to this channel. Wait for the notification when I start talking of the next step, which is very important, which is actually because this is just a mixture of 238 and 235 in a very small percentage. You need to get that 235 out. And that process itself is known as uranium enrichment. It's a part of physics, but it's very interesting how this process is carried out. So we'll come to that next time. Till we do that, namaskar from Prakash Zo.